All right, so I'm going to go through proof 3.2, which is basically kind of a geometric variant of the Hahn-Banach extension. So what we do is we start off with a convex set K, and this convex set is such that its interior contains the zero vector. Now, V is some linear variety that's in our big set X, our norm space X, I should say, but it contains no interior points of the convex set K. And we're going to define a linear functional f such that f is equal to 1 when it's evaluated for any point x of our V linear variety. Now, since V does not contain any interior points of k, we know that we have f of x is equal to 1 for any x element of V, which is less than or equal to the Minkowski functional of k, because the Minkowski functional of k, it's greater than or equal to 1 for any boundary point or anything outside of the set K. It's only less than K when we're looking at points within the interior of K. So the first part of this proof is just to show that our function f of x must be less than or equal to p of x when we're looking at any x which is an element of the subspace M that is generated by our linear variety of V. So we have this fact that V is generating M. We also know that f is a linear functional. So f is therefore defined on M because of the fact that, the kind of linear combinations of vectors in V generate M, and so we can just apply that with the linearity of f, and we will get function values from that. So we know, here's an example of that for any V, small v element of our linear variety big V, we have that f of V must be equal to 1, which is less than or equal to p of V. And then we know if we have an alpha that's greater than 0, we multiply that by original V. By linearity, we get this. So this is just alpha times 1, which must be less than or equal to alpha times p of V, which is equal to p times alpha V. We do the same step except for alpha less than 0. And so what we've shown by doing this is that for any point, for any element of the subspace M, we have that f of M must be less than or equal to p of M. I think one step that's not included in Paul's notes here is the case of alpha is equal to 0. But of course we know that when we're evaluating the Minkowski functional at the 0 vector, it's equal to 0. And likewise for any linear functional evaluated at the 0 vector is equal to 0. So I think that goes without saying perhaps. Okay, so now we're going to look at big F, which is the Hahn-Banach extension of little f, the functional to all of our norm vector space V, X, excuse me. We need to show that f is continuous, and we're going to show this by taking advantage of the fact that a linear functional that is bounded is continuous. And so we note that at p of x, actually, we're not going to use the bounded condition. We're going to show that if a function is continuous at one point, a linear functional is continuous at one point, I should say that it's continuous everywhere, and we'll show that it's continuous at the 0 vector. So we know this is the case just by the fact that when we've constructed our Hahn-Banach extension, it must respect this relationship, this inequality. And we also know that if we have x going to the 0 vector, p of x goes towards 0. And so we take these things again, and then we also know that f of x must be less than or equal to p of x, but also negative f of x is equal to f at evaluated at negative x, which again has to be less than or equal to p of negative x. And so we have the absolute value of f of x goes to 0 as x goes to the 0 vector, and that shows that our Hahn-Banach extension f is continuous at the 0 vector and hence continuous everywhere. The next part of this is to show that the hyperplane of all the points x such that our Hahn-Banach extension is equal to 1 is closed and contains no elements of the interior of our convex set K. Again, this is pretty simple. We have the sequence x of n, which is an element of H, then we have it converging to some x. And because f is continuous, which we just showed, we can take the limit inside and outside, and so we know that f of x, which is equal to the limit of n going to infinity, etc., is equal to 1, so x has to be an element of H. And we also want to show that this H doesn't contain any interior points. Well, we know that all the x's that belong to H, we have f of x equal to 1. And we also know that f of x must be less than or equal to p of x. So this means that 1 is greater than p of x for all of the x that are elements of H. And by the definition of the Minkowski functional, this means that H does not include any interior points of K. And if we restate this in terms of the dual space, we know that there's some vector x star element of the dual such that when we're looking at any element of the linear variety V, we have that it's going to be equal to 1 when we evaluate it using our inner product. And likewise, if we do the same thing but with some element K of the interior of K, we get that it's less than or equal to C, which is equal to 1 here. So that's the whole proof.